Hello. In this video, we will cover velocity and acceleration. To introduce the topic, recall that the velocity is the change in position per a change in time. If we recall from Calc 1, if we have a position function, then the velocity is equal to the derivative of that position function. Okay, and when we go through and write this, velocity equals the derivative of position, and we write it in this format, you can clearly see that we have a change in position in the numerator, right? So if s is position, then ds represents a change in position per a change in time in the denominator here. Right, so we have ds dt, but that's our format for the derivative. It represents the fact that we have a instantaneous change in s per change in t, in our formula. Okay, so we can go through and use our understanding from Calc 1 to go through and define velocity in terms of vector functions. So to do that, let's say r of t defines the position of a particle. If r of t defines the position of a particle, then r prime of t, which would equal dr dt, right? These are just different formats representing the derivative, would equal the limit as h goes to 0 of r of t plus h minus r of t over h. And if we look at that format, whether you want to look at dr dt, right? If r is the position, then dr would be a change in position. If you want, whether you want to look here or if you want to look over on this side, using the limit definition, we clearly have r of t plus h. That's going to be the position at time t plus h. And then we have r of t, which is the position at time t, and we're subtracting them. So the difference here, we're going to end up with a change in position. Now the difference between the format that we've got here with vectors and the format that we had here back in Calc 1 was that with vectors, we have multiple components in terms of the change in position. You could have a change in position for x and a change in position for y, whereas the change in position from Calc 1 was a one-dimensional change. With vectors, we could have a two-dimensional change, both x and y change in position. And then h, it might not be apparent just at a glance that h is a time, but the fact that we combined h with t inside of the input here tells us that the denominator here, h, is a time. We're adding some amount to the time value, and so that's going to be time. So we're going to have change in time here in the denominator, and that's also apparent if you kind of look at dt, right? So we've got dr, which is change in position, over dt, which is change in time. And as we defined it, velocity is change in position over change in time. So this is velocity. It's just velocity as a vector instead of as a scalar quantity. Okay. In terms of the way in which the velocity vector behaves, the velocity vector is still a tangent vector. And it can be interpreted as the direction of the movement of the particle. At time t. So if we were to sketch a picture for that, okay, so the idea is we have a curve, and that curve is the position, r of t, okay? And then we go through and we calculate the derivative of r, and that derivative is going to be a change in r over a change in t. And let's just say we go ahead and put that on here at this point here, and that derivative is going to be a vector, right? And it represents the way in which r is changing in the x direction, which is relatively small, and the the x direction, which is relatively large, and the y direction, which is relatively small in this case. So it represents the change in position over the change in time. It can be interpreted if this is the direction of increasing t, right? So if the vector function has arrows like this, that it's being drawn in this fashion, then at this point right here, you can interpret the vector. We'll say this is time t. You can interpret the vector to be the way in which the particle is moving. It's the change in position, okay, but also it has a time component over a change in time. Okay, so it's the direction that the particle is moving in at time t. Okay, so you get this, the vector aspect of velocity allows us to not only have how fast the particle is moving, but also the direction the particle is moving in both the x and the y direction. Okay, as far as interpreting how fast the particle is moving as a scalar quantity, we also can go through and do that. The velocity vector can be turned into a scalar by taking its length. Okay, and that resulting speed is going to be, we can go through and use our traditional understanding of how to go through and interpret that speed, because it will be a scalar quantity, so like miles per hour. And the way in which you can kind of go through and prove that to yourself is if we start off with this result, the length of v, and we go through and replace it with what it's equal to, which is equal to r prime of t, right? From the previous page, we said r prime equals v. Then as you may recall from a previous video, we said the length of R, we went through and showed that the length of R prime like this is actually equal to ds dt. And so this enables us to go back and turn our velocity vector into a traditional speed result that we can go through and interpret. Okay, and so that's the velocity vector altogether. It gives you how it tells you how the particle is moving at a particular time. It also can tell you how fast the particle is moving at a particular time. It can be broken up into components, and so you can see how much the particle is changing in the y direction and how much the particle is changing in the x direction. So it can do all of that, right? So the results that we had from Calc 1, the one-dimensional results for going through and interpreting position and velocity, can be expanded to a two-dimensional version by using vectors, or 3 dimensions if you had a particle moving in 3 dimensions. Okay, so to expand upon that, just like in Calc 1, when we went from position to velocity, the next thing that we went through and defined was we defined the acceleration as the change in velocity over time. So due to that fact, you can also do the same thing except for vectors. And using a similar result to the one that we did on the previous page, we can go through and say that the acceleration equals the derivative of velocity. And then since the velocity is the derivative of position, we can say that acceleration is the derivative of position, the second derivative of position. Okay, so let's go through and do an example so we can see how this works. So let's suppose that we are given the position function for a particle, and it is equal to 3t squared I plus 7tj plus the natural log of tk. And we're told to find velocity, acceleration, and speed when t equals 3. All right, so first we can go through and find the velocity function by taking the derivative of position. And as we discussed in a previous video, the way that you calculate the derivative of a vector function is just by taking the derivative of the components. So we take the derivative of 3t squared, which gives us 6t. The derivative of 7t would be 7. And the derivative of natural log t is 1 over t. And then we can go through and find the acceleration vector. That's equal to the derivative of the velocity vector. And we take the derivative. So to take the derivative of 6t, we get 6. The derivative of 7 is 0. The derivative of 1 over t is going to be minus 1 over t squared. And so that gives us the acceleration vector. And then to go through and find the speed, you can go through and find the length as a function, but typically it's easier to go through and find the velocity vector and then just find its length to calculate the speed. So let's just do the speed in a minute. All right, so now that we've got the velocity and acceleration, we can find those when t is 3. So the velocity when t is 3 would be 18I plus 7j plus 1 over 3k. The acceleration when t is 3 would be 6I minus 1/9 k. And then to go through and find the speed, we can just find the length of the velocity when t is 3. And so you do square root, and we get 18 squared plus 7 squared plus 1/3 squared. And if you go ahead and multiply that out and add it, you should get square root of 3358 over 3. Okay. And so, so speaking of how to interpret these results, right? So first of all, the position, this gives us the position of the particle at any time. And you can go through and you can plug in time values and you can trace the particle as it moves through three-dimensional space. All right, the derivative here is the velocity vector. So this tells us how the particle is moving at any given point. We can tell the direction the particle is moving in, right? It's moving in the direction of 6t, 7, and 1 over t, right? And also it tells us how fast the particle is moving by the length of the vector, right? We can go through and divide by its length. Or we can go through and calculate the magnitude or the length of the vector. And that will give us how the speed of the vector. And then finally, we can go through and calculate the derivative of velocity. This gives us the acceleration. And so this tells us how the velocity is changing. So it tells us that per unit of time, the velocity is increasing by 6 units in the x direction every increment of time. And it's changing -1 over t squared increments in the, per increment of time in the k direction. And so you can go through and not only see how the position is changing as a whole, but you can break it down into components. You can see how the x direction is changing, how the velocity is changing in the x direction by looking at the I component, and same thing for j or k. Okay. Next, we're going to look at it is just like in Calc 1, we can reverse the process. Right? We can reverse the process to go from acceleration to position. And one way that you could see that is if we started with acceleration, we know that acceleration equals the derivative of velocity, which you could instead write in this format, right? dv dt, which you could also write in this format as the derivative of velocity, right? And then if you went through and integrated both sides, right, of this, if you have the integral of a of t dt, that would equal the integral of the derivative with respect to t of v dt. Then the integral of acceleration would equal, on this side, the integral of the derivative, the integral and the derivative are inverse functions. They cancel each other out, and we end up getting v plus c. And so we can go through, actually, let's throw a t in there, v of t plus c. And so you can see that by integrating acceleration, we can get to velocity. And similarly, if we integrate velocity, we can get back to position. And so the process can be reversed by going through and integrating, finding the indefinite integral or the antiderivative. We can reverse the process. So if you differentiate to go from acceleration to velocity to position, then you find the antiderivative, or you integrate to go from position to velocity to acceleration. And you can just reverse the process. Let's see an example with that. given that the acceleration is equal to ti minus sine tk, where v of 0 equals I plus j, and r of 0 equals negative 2I plus k. Find velocity and position vectors. For time t, all right, for any time t. Okay, and in order to do that, what we're going to do is we're going to integrate acceleration, and that is going to give us velocity. Okay, so we're going to have the integral of ti minus sine tk. Right, and as we discussed in a previous video, the way that you integrate is component-wise. So we're going to find the antiderivative of t, so that will be t squared over 2. The antiderivative of negative sign will be positive cosine. And then we have plus c. And just to mention, the plus c here is a vector c, right? So, and the reason for that, okay, is that what does the plus c represent when you're going through and you're finding an indefinite integral? It represents the constants that would go away if you went through and took the derivative of this, right? The antiderivative of ti minus sine tk is the function that you would differentiate that would get you ti minus sine tk. And that's this function with this plus c representing any potential constants. And the c enables, by putting a plus c like this, it enables us to handle both ith components of things that are multiplied by I constants and j and k all at the same time. So it's just encompassed into this. If you wanted to, you could do a plus ci plus dj plus ek or something like that and split up the components, but nobody does that. You don't have to do that. It's just, it would be an option if you found the idea of adding a constant vector confusing. Anyway, so once you've gone through and you found the velocity and it's got this plus c, then what we're going to do is we're going to use our initial condition to figure out what c is. So if you plug in 0, what's going to happen here? We're going to get 0i. We're going to have plus k. Okay, because cosine of 0 is 1. And then plus c. And then what else is v of 0 equal to? It's equal to I plus j. So we have I plus j equals k plus c. And so I plus j minus k equals c. And then if you plug those in, we get v of t equals t squared over 2i plus cosine t k plus I plus j minus k. And then at this point, the way that you want to handle it is you want to combine the different components, right? So if we've got t squared over 2 is 2i, and we've got 1i, so we can just combine those. T squared over 2 plus 1i plus j plus cosine t minus 1 k. Okay. And then next, to go through and find position, we would want to integrate that. So r of t equals the integral of v of t dt. So that's going to be the integral of t squared over 2 plus 1i plus j plus cosine t minus 1 k dt. And so next, so to do that, so we'll have the antiderivative of t squared over 2 is going to be t to the third over 3 times 2, which will be 6. Antiderivative of 1 will be t. Antiderivative of 1 will be t. Antiderivative of cosine is sine minus t plus c again. And then r of 0, if we plug in 0, what happens? We're going to get 0 here, 0 there. So 0i, 0j, 0, 0, 0k. So we're just going to get c. And then we know from the, if we go back to the previous page, what was r? R of 0 was negative 2i plus k. So we're going to get negative 2i plus k equals c. And then pop that in, and we get r of t is t cubed over 6 plus t I plus tj sine t minus tk minus 2i plus k. And then you can just combine those, right? So we've got a negative 2 that goes with I, so put that with these other i's. Leave j alone. Then we want to add 1 to the k components here. So we've got sine t minus t plus 1. Okay. And there you go. So that's how to go through and reverse the process given acceleration to get to position. Okay, next, we're going to go through and look at an application of velocity and acceleration. This application is called projectile motion. And what we're going to do is we're going to suppose a projectile is fired with angle alpha and initial velocity v naught. Well, let's call that initial speed. Because that's a scalar quantity. And we're going to turn that into a vector in a few minutes. Next, we want to go through and find the position function for any time. We're told to ignore air resistance. This is a simplified model. And the only force acting on the object is due to gravity. Okay, so how could we go through and, given this information, create a position function, right? That's what they're asking for, a position function, knowing only that the projectile is fired with an angle of alpha and an initial speed of v naught. Okay, well, the way that you go through and do this is we use Newton's second law. You start with. This is the way that you start. So Newton's second law of motion says that the force that acts on an object is equal to the mass times the acceleration, the net force. We should say the net force is equal to mass times acceleration. Now, what forces act on an object? Well, if you actually read the question, it tells you ignore air resistance. The only force acting on the object is due to gravity. right? So what would be the gravitational force, if you wanted to think about it that way? So the force due to gravity, right, we know is equal to the mass times the gravitational constant. And so you can represent that as a g, right? And that's negative in that it's, we're going to treat that as negative. So negative is going to be downward in our system and positive is going to be upward. So if you can leave this as positive, but then when you go through and you create your system, what you're going to have is you're going to have that down would be positive and up would be negative, which would be a little weird. So we're going to put a negative on there to denote the fact that gravity pulls objects downward. Okay. And just for this example, I'm just going to go ahead and pop G in there as negative 9.8. So we're going to end up with negative 9.8 times the mass would be the force due to gravity. And so if we don't have air resistance, we have no other forces, then if the net force acting on an object is mass times acceleration, and the gravitational force acting on the object is negative 9.8 times the mass, then you can just set those two equal. So we get mass times acceleration equals mass times negative 9.8, and then the masses end up canceling, and we have the acceleration at any time. Oh, whoops, hold on. Made a mistake here. So the whole point of using vectors is that we can denote directions. And so if you think about the way that this negative mg is acting, it's going to be acting in the j direction, right? It's not acting in the I direction. It's not, the objects are not pulled in the x direction, they're pulled in the y direction, right? If we have a model, right, where we go through and we have an object, and so we have x is the horizontal and y is the vertical, then an object that is moving through space, gravity is pulling it downward. Gravity does not affect it in the x direction. So we're just going to have negative 9.8 times the mass times j. Okay. So we get negative 9.8 j, and let's throw a j there. There we go. Okay, so that's correct now. And so once we have acceleration, just like we did on the last example, we can go through and we can use the acceleration function to find the velocity. So we can say that the velocity of the projectile is going to be the integral of the acceleration, which equals the integral of negative 9.8 j, which we can go through and find that. So that's going to be negative 9.8 t plus c. Now in this case, so c is the represents could represent the velocity at any time. It's an initial velocity. All right, so we need an initial velocity to go through and set that. So that could be the velocity at time 0, or it could be the velocity at some other time. In this case, we actually have the velocity at time 0. So if we go through and say, so v of 0 is going to equal, so plug in 0 for t, you get negative 9.8 times 0. That's going to be 0 plus c. So we know that v of 0 is equal to c. The question is, what is v of 0? What is the initial velocity? As a vector, right? As a vector. Well, if we go back and look at the information they gave us, right, we were told that the initial speed is v naught and the angle is alpha, and you need to go through and use both of those two together to figure out what v naught would be, or sorry, what the velocity vector at time 0 would be. So let's go through and see if we can figure that out now, right? If you draw a picture, and you're told the projectile is fired at an angle of alpha, and you're told that the speed is v naught. Well, keep in mind that what is the speed? It's the length of the velocity vector. This is the velocity vector. So v naught would be the length of that vector. Now this is a scalar, so it's the length of the vector. Okay. to go through and turn this into a velocity vector, instead of just having an angle alpha and a length of the velocity vector v naught, we need to go through and use some trigonometry, right? So we know, for example, that if we went through and just kind of dropped down this, right, we can go through and we can find this distance and this distance just by using trig. And so if we go through and let's call this x and let's call this y, then sine of alpha, right, is going to equal opposite over hypotenuse. So we're going to get y over v naught, and then y will equal v naught sine alpha. And then we could do something similar with cosine. Cosine of alpha equals x over v naught. So x would equal v naught cosine alpha. And so by doing this, we've actually figured out what the velocity vector would be at time zero. So v at zero is going to equal v naught cosine of alpha I plus v naught sine of alpha j. And now we can take those and pop them in here. Maybe we'll do that on the next page. So we finished up, we're at v naught equals c. And so v naught is equal to, or v of 0 is equal to v naught cosine alpha I plus v naught sine alpha j, and that equals c, right? So all I've done is just, we kind of got to this point. We said, oh, wait, what is v naught? Took a pause, figured that out, and now we're picking up here where we're just substituting v of 0 on the left-hand side. Okay, and so once we've done that, that gets us what c is, and now we want to take that c and plug it into our velocity vector function. So our velocity vector function is negative 9.8 tj plus c, and then we just figured out what c is. So we're going to have negative 9.8 tj plus v naught cosine alpha I plus v naught sine alpha j. And then if we combine the components here, so we're going to get v naught cosine alpha I plus v naught sine alpha negative 9.8 t j. Okay, and so once we've got that, next we can go through and we can find the position function by integrating the velocity function. And so we'll have the integral of v naught cosine alpha I plus v naught sine alpha minus 9.8 t j dt. That gets us v naught cosine alpha t I, and then plus, if we antiderivative this, is going to be v naught sine alpha t, and then minus the antiderivative here will be 4.9 t squared j plus c. Okay, and then if we plug in 0, r of 0 is going to equal, now we're plugging in 0 for t, so don't get confused here. We're not plugging in for alpha. Alpha and v naught are going to be given depending in each individual problem you work on. They're going to be given in that problem. So they're going to change from problem to problem. And so the t quantity is what we're plugging in for. If you plug in 0 for t, it just wipes out this, wipes out this, wipes out that, and so we just get c. And now what we're going to do for this, right, is it's unspecified in the projectile motion problem, what the position is of the object. So you could guess, is the position fired from the ground? Is it fired from on a hilltop? There's just any number of possibilities. Is it fired off of a building? And so what you can do for this is you can go ahead and just say, you know what, I'm going to say that r of 0 is x naught I plus y naught j, where x naught is the x position and y naught is the y position. Now, typically x naught will be 0. You'll position the object so that you're firing where x naught is 0, but you may fire off of a hill or a building or some other thing where y naught might not be 0. And so if we go through and just choose x naught I and y naught j like this, then if you take those and plug them in, you'll get r of t equal v naught cosine alpha t I plus v naught sine alpha t minus 4.9 t squared j. Oh, I didn't really leave myself enough space here, plus x naught I plus y naught j. And then if you go ahead and rewrite it, combining components, we're going to have the x naught is going to go with the I, so we'll have x naught plus v naught cosine alpha t I, and the y naught goes with this. Y naught plus v naught sine alpha t minus 4.9 t squared j. And that gives us the answer. Okay, so the question was go through and, or not the question, but the goal was to go through and find the position function, and we have done that. This would be the position function for any time. Okay. So let's go through and see if we can do an example using all of that. All right, suppose a projectile oops. So let's just do the whole thing over again. A projectile is fired with a muzzle speed of 150 meters per second at an angle of elevation of 45 degrees from 10 meters off the ground. Where does the projectile hit the ground? And at what speed? Okay, so we can go ahead and just start off by just grabbing our position function here. So we have r of t equals x naught plus v naught cosine alpha t I plus y naught v naught sine alpha t minus 4.9 t squared j. Okay, that looks right. And now we want to figure out what all of these different variables are going to be. Okay, so looking up at the problem, x naught and y naught, that's the position of the particle. We just finished talking about that. So the position of the particle, typically you just go ahead and say the position of the particle. You have to have a good reason to not make this 0. So we're just going to have the x position of the particle be 0. And we'll have the y position. So this is the x, the amount of units in the x direction you are from, in your problem from where you're firing. And then this is the number of y units. So the y units in this case, we're told the object is fired from 10 meters off the ground. So that's going to be 10. And then v naught is the initial speed. And the initial speed we're told is 150, right? It's meters per second. So we'll just remember that. And we're told the angle of elevation alpha is going to be 45 degrees. Okay. And so that, okay, that looks like everything. So now you can just take all that and plug it in. And what's going to happen? So we're going to have, so 0 there. We've got 150 times cosine of 45 degrees. That's going to be 75 root 2 ti. And then here we're going to have 10 plus, so we've got 150 times sine of 45 degrees. That's also going to be 75 square root 2 t, and then minus 4.9 t squared j. And that gives us our model for the problem. All right, so now with that model, can we go through and answer the questions? Oh, and if you wanted to, you could go through and draw a picture too. So I did draw a little picture. All right, so what does this look like? We've got our object, and it's sitting here. It's 10 meters off the ground, and it's being fired up into the air, right? We know that the angle is 45 degrees, and the speed, the initial speed, which is the length of this velocity vector, is 150. So there, that might help to wrap your mind around the problem. Okay, so how do we go through and answer the questions? What are the questions? Where does the projectile hit the ground? So where, right? So the information here, this gives us the height. This gives us the x direction, the number of units in the x direction. So it's really asking, right? Obviously, when it hits the ground, the height is going to be 0. So it's really asking what this is going to be when it hits the ground. Okay. So in order to figure out what this will be when the object hits the ground, the way that you can go through and do that is you can find out, well, you can find out when it does hit the ground. What's the time value for when it hits the ground? If we have the time value for when it hits the ground, then we can go through and plug that into this, and it will tell us how far it went in the x direction before that occurred. All right, so this, again, this is giving us the units in the x direction. It's really asking a question related to this. It's asking how far or what the quantity is here when it hits the ground, but we can't answer that until we know what the time value is when it hits the ground. So you really want to start over here with the height, right? So they can think about it this way. So the object is fired and then it comes down, crashing down, and this is where it hits the ground. But what we want to know is what the time is there. And then once we have that time, we can then we can plug it into this and find that. So we want to start off with the y position. So we've got 10 plus 75 root 2 minus 4.9 t squared. And what we want to know is we want to know when that's going to be 0. When we want to know when the height is going to be 0, right? So this is the x, this is the height, and so we want to know when the height is 0. So take it, set it equal to 0, and then we just want to go through and solve. So you can go through and use the quadratic formula. We will get negative 75 root 2 plus or minus the square root. We'll get 75 root 2 squared minus 4 times negative 4.9 times 10 all over negative 4.9. And if you go ahead and plug that into a calculator, you're going to get two quantities. We're not interested in the negative value. Why not? Okay, let's actually go back to the picture that we drew here. If you went backwards in time and just kept going here, yes, the object is going to hit the ground somewhere back here if that were possible. If you could fire the object and it went in the opposite direction from where the direction you're aiming the the gun that's firing the object, the muzzle speed. if that were possible, we could have a negative time value, but that's not possible. We're firing the object this way, and so we're only interested in positive time values. And so when you go through and calculate this, the plus or minus, you're going to get a negative solution, just pitch it. We're only interested in the positive solution, which is at 21.74, approximately 21.74 seconds. Okay, so now once we have the time when the object hits the ground, we can then go through and use this portion of the vector to figure out what the x position would be. And so if you go ahead and take that, we're going to get that x equals 75 root 2 times t, or x equals 75 root 2 times 21.74, which is approximately 2,305.88. And since our velocity is meters per second, so this is going to be meters per second times seconds, so we're going to end up with meters. Okay. And then what else does it ask us to do? So it says, at what speed does it hit the ground? Okay, at what speed? So how could we go through and find the speed when it hits the ground? Well, we have, if we just take a step back, right, go back to our previous page here, we have, this is the velocity. So this ended up being the position function, but we had a velocity function at any time. And so we can go through and find the velocity when the object hits the ground. And once you have the velocity vector when it hits the ground, you can use that to convert into speed. Okay, so we could go through and do, we know that v of t equals, wait, what did it equal? So it's v naught cosine alpha, and then v naught sine alpha minus 9.8t. Okay, and that looks correct. And then we can go through and plug in v of 21.74. Oh, wait, hold on. So you do need to substitute in, right? So v naught is 150. Cosine alpha is root 2 over 2. Here we're going to get 150, root 2 over 2, and then minus 9.8 times 21.74. Okay, so if you simplify that, that's going to be 75 root 2i plus 75 root 2 minus 9.8 times 21.74 j. Okay, so that's the velocity when it hits that's the velocity vector when it hits the ground. So we know it's moving at 75 root 2 per unit of time in the x direction, and whatever the result of this quantity is in the y direction. So to figure out what the actual speed is of that in terms of a scalar quantity, we need to convert it from the velocity vector that has this x component and a y component into the scalar quantity. And so you can do that by finding the velocity, find the length. And so the length is going to be the square root of 75 root 2 squared plus 75 root 2 minus 9.8 times 21.74 squared. And if you go through and punch that into a calculator, you get approximately 151. And so the speed is in terms of meters per second. And you could compare that to the launch velocity. So it was the muzzle velocity when the object was launched was 150, and when it hit the ground, it was 151. The fact that the two are so similar is not a coincidence, and that's because the object is not very high off the ground. If the object is fired from the ground, then the velocity, upward velocity when it's fired and the downward velocity when it hits the ground are the same. So the 10 doesn't give it much more time to pick up more speed. If you launched it off the top of a building, then you could potentially have a larger final velocity when it hits or final speed when it hits the ground. Okay, so that's the video. So that's our video on velocity and acceleration. Thank you for watching. See you next time.